We are in section 3.4, optimization and elasticity of demand. A function may have more than one relative maximum or minimum. It may be important in some cases to determine which value is either the largest or the smallest. Remember, relative extrema were discussed in section 3.1, and we had relative extrema or local extrema, which were our local mins and maxes or relative mins and maxes, which occurred anywhere where our function switched from increasing to decreasing or vice versa. And so the next definition that we have is called an absolute maximum, and then we have an absolute minimum. So an absolute maximum is going to be the largest possible value of a function, and it can be an endpoint. And an absolute minimum is the smallest possible value of a function, and this also can be an endpoint. So we have a graph to the right which shows our relative minimums, and then it also shows our absolute minimum, which is the smallest of the small. Our function does not have an absolute maximum because if you notice, our endpoints are both extending upwards, and so there isn't an absolute maximum that would occur. The next thing that we have is extreme values or extrema of a function f of x are the absolute maximum and minimum values of the function. Singular would be extremums. And so for this, anytime you see the word find the extreme values or find the extremums, it would mean to find the absolute maximum and minimum. So it says let f of x be a function defined on the domain D. We say f of c is the absolute minimum of f of x if f of c is less than or equal to f of x for all x values in our domain. The absolute minimum is going to be the smallest y value over the entire domain, and we cannot use negative infinity. So this is going to be the smallest value that we would have for our y values. And likewise, the absolute maximum of f of x is going to be where f of c is greater than or equal to f of x for all x values in D. The absolute maximum is the largest y value over the entire domain. And again, we cannot use infinity, and so this would be the largest y value. So right below this we have what's called the extreme value theorem, and this says that if f is a continuous function on a closed interval a to b, then f obtains an absolute maximum value f of c and an absolute minimum value f of d at some number c and d in that interval. And so it could be, from the pictures given right below, it could be endpoints for those absolute maximums, or global is another way to say this, maximums and minimums. And likewise, as with having this not be the endpoints, but being somewhere in that interval that was given. So it doesn't have to necessarily be the endpoints, it could also occur within that interval. So right below this we have the closed interval method. So this one says to find the absolute maximum and minimum value of a continuous function f on a closed interval a to b. We first need to find the values of f at the critical numbers of f on a to b. So the first thing is to find our critical numbers. Make sure critical numbers are in the interval, which is one of the important things here to note. 2 says to find the values of f at the endpoints of the interval. And then 3, the largest of the values from steps 1 and 2 is the absolute maximum value, and the smallest of these values is the absolute minimum value. So again, what we need to do is find our critical values, and you need to make sure that those critical values are in that interval. So sometimes the interval might be from 0 to 2, but your critical value is -7. So do not include that because it's not in that interval. And then the next thing you need to do is find your critical values and substitute these in to find the y values for these. So the height would be what you're finding, that maximum, the height of it, or minimum part. And so once you have your critical values, we need to substitute into our function f of x. And likewise, we need to do that also with the endpoints. So substitute endpoints into f of x. And then the largest of the large and the smallest of the small are going to give us our absolute max and our absolute min. So the next example has a graph given to us, and it says find the location of any absolute extrema for the function below. So if you notice on this function, we have no absolute max. So no absolute max. And the reason why is because our right endpoint is an arrow, and that means it goes on forever upwards, so we don't actually obtain a maximum point. Our absolute min is going to be the smallest point that we have, and notice that this time our endpoint on the left side is not extending down forever to negative infinity. So the smallest value that we actually have is this point down here. And so -1, -3 is going to be our absolute min. So the next example that we have says find the absolute max and minimum of f of x equals, and it's 2x cubed minus 15x squared plus 24x plus 7 on the interval from 0 to 6. So again, the first thing that we're going to do is find our critical values, and in order to do that we need to take a first derivative. So taking the first derivative of our function, we get 6x squared minus 30x plus 24. And we're going to set this equal to 0 in order to find our critical values. Also note that we don't have any places where our first derivative is undefined. And also note that we're dealing with a continuous function over that interval from 0 to 6. So from here, I can factor out a GCF, which would be 6, and so we have x squared minus 5x plus 4 equals 0. And then this would factor using our guess and check method. And so we have 4 and 1, and they're both going to be negative since our middle term is negative. Solving each of these factors by setting them equal to 0. We get x is equal to 4 and x is equal to 1. And so these are both our critical values for this problem. And our endpoints were given to us. They are at 0 and at 6. So we need to find the value of our y value for this function when x is equal to 1, when x is equal to 4, and then in addition at our endpoints, which is at 0 and at 6. And so again, these are our critical values. These are our endpoints. And so substituting a 1 into our original equation, which again is typed and given to us up above, we're going to see that f of 1 equals, when you work this out, to 18. F of 4 works out to be -9. F of 0 would work out to being 7. And f of 6 works out to being 43. So now you have these y values that we just calculated here. And you're going to select the largest of the large. And the largest of the large is 43. And so this is going to be our absolute max. And our absolute min is going to occur when x is equal to 4, and that's -9. So this is going to be our absolute min. And so our absolute max is going to occur at the point of x is 6 and y is equal to 43. And our absolute min is going to occur at x is equal to 4 and y is equal to -9. For this problem, I did give us the graph, which is given to the right. And you'll notice that at 6, we get the value of 43. That's that endpoint. And that would be our absolute max. And likewise, at 4, we get that absolute min, which is at -9. So the example right below, I'm going to go ahead and circle, and we'll try this one together in class. And then the next example that we have says find the absolute extreme on the function f of x equals x minus 1 over x squared plus 1 on the interval from 1 to 5. So again, we're given our endpoints of 1 and 5. And so the first thing we need to do is calculate our first derivative. And so in order to do that, we have to use the quotient rule. And so we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all over the denominator squared. And then from here we can simplify this and we have x squared plus 1. Distributing my 2x and also my negative, we have negative 2x squared plus 2x all over x squared plus 1 squared. And then again, combining our like terms for this problem, we arrive at negative x squared plus 2x plus 1 all over x squared plus 1 squared. And so in order to find our critical values, we're going to set this equal to 0. And doing that, I can multiply both sides by my denominator, and I'm left over with negative x squared plus 2x plus 1 equals 0. Using the guess and check method, you'll see that this does not factor nicely. And so in order to solve this, we're going to use the quadratic equation. And so we have x equals, and it's negative b, so negative 2 plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And from here we can clean this up. We get negative 2 plus or minus the square root of 2 squared is going to be 4 minus 4 times negative 1 times 1 would make this positive 4 all over negative 2. And so from here we have negative 2 plus or minus the square root of 8 all over negative 2. And square root of 8 simplifies to 2 times 4. So the square root of 2 times the square root of 4, and the square root of 4 is just 2. And so we can rewrite this as negative 2 plus or minus 2 square root 2 all over negative 2, which is going to be equal to negative 2 over negative 2 plus or minus 2 square root of 2 over negative 2, which simplifies to 1 plus or minus, and dividing by that negative just switches the plus and minus, so it doesn't change anything. So the 2's would reduce, and then we just say rad 2. And so these are our x values that we have, and looking at the decimal values of these, you can leave them as this, but we'll just go ahead and round. And so we have 2 values, and you can add 1 plus rad 2, and you get 2.41, and then subtracting, you get negative 0.41. And so these are our critical values that we get. So substituting in your critical values, we are going to substitute these into f of x, which is given to us up above. And so we're going to substitute in 2.41. And looking at my second critical value, you'll notice that negative 0.41 is not in my interval from 1 to 5. So is not in the interval from 1 to 5. So that means that we don't include it. So I'm not going to write that one down to check. The next value that we need to check is going to be coming from my endpoints. So we have f of 1 and f of 5. And again, we only have one critical value that we're checking because that's the only critical value that's in that interval. And then the other 2 values that we're checking are coming from our endpoints. And so substituting this into f of x, which is circled up above, substituting in 2.41, we get 0.21. And substituting in 1, we get 0. And substituting in 5, we get 0.15. So from here, your absolute max is going to be the largest value that we have, which is 0.21. So this is going to be our absolute max. And our absolute min is going to be the smallest value that we have, which would be 0. And so we get an absolute max at x is 2.41, or you can write it as the radical expression down below, and our y value would be 0.21. And we also have an absolute min at, and our y value is 0 and our x value is 1. And so there is our absolute max and our absolute min for this problem. For an open interval, rather than evaluating a function at the endpoints, we evaluate the limit of the function to see where the endpoints are approaching. And this is coming back from chapter 1. So we're going to be looking at the limit as x approaches either positive or negative infinity, depending on what we're given, of our function. So the example right below this says, find the absolute extrema, if they exist, as well as all values of x where they occur for f of x equals, and it's 12 minus x minus 9 over x, and it does tell us that x has to be greater than 0. So for this problem, I don't have a closed interval. So we do have an open interval, meaning this is going from 0 to infinity. And notice that it doesn't actually equal 0. So in order to do this, we first need to find our critical values. And to do that, we have to take a derivative. And in order to do this also, I need to rewrite my equation that we have. And so we have 12 minus x minus 9x to the negative first. So taking a derivative, we have negative 1 and then plus 9x to the negative second. And setting this equal to 0, I'm going to go ahead and put my exponent, the negative 2, as a positive value. So I have negative 1 plus 9 over x squared equals 0. I'm going to add 1. And I have 9 over x squared equals 1. Multiply both sides by x squared. And then taking a square root, we get x equals plus or minus 3. And so these are our possible critical values. Again, looking at this, we need to notice that x has to be greater than 0. So the negative value for my x, the negative 3, would not work. So I'll put down x equals 3. X equals negative 3 is not in interval. Okay, it must be a positive value. And then we also need to look at the value that we get for this, which would be f of 3. And we don't have endpoints for this one. We actually have to look at the limit. So as stated up above, so we have the limit as x approaches infinity of my function, which is 12 minus x minus 9 over x. And then also we need to look at as it's approaching that other endpoint, which for us isn't negative infinity, it's approaching 0. And notice it's not equal to 0, it's approaching 0, and it's approaching 0 from that positive side. So we're going to say the limit as x approaches 0 from the positive side, or plus from the right, of 12 minus x minus 9 over x. So the first one that we have is f of 3. And finding f of 3, substituting this into our function, which is given to us up above, we get a value of 6. And then evaluating the limit as x approaches infinity of 12 minus x minus 9 over x, we get 12 minus infinity minus 9 over infinity, or just 0. So this works out to be negative infinity. And then the limit as x approaches 0 from the right of 12 minus x minus 9 over x is going to equal 12 minus 0 minus 9 over 0, and 9 over 0, and I should say from the right, is going to be equal to infinity. So this will be 12 minus 0 minus infinity, or just equal to negative infinity. And so the largest value that we have for our y value would be 6. So this would be our absolute max. And then since both of our n values, as the limit as x approaches infinity and as the limit as x approaches 0 from the right, both approach negative infinity, so they're going downwards towards negative infinity, that means that there is no absolute min. Remember, infinities don't count. It has to be an absolute maximum point or an absolute minimum point. And so we have a absolute max at 3, 6, and no absolute minimums. So the next thing that we have is called the second derivative test to find absolute extrema. And so this one says, let C be the only critical number of f of x, and suppose the second derivative is continuous near C, and the first derivative it's equal to 0 at C. And it says if f double prime of c is greater than 0, and that means that if the second derivative is greater than 0, we have a concave up function. This means that we have an absolute minimum on that interval. So the second one, draw over here. This one says if our second derivative is negative, that means that we have a concave down function, which means that we have an absolute maximum on that interval. So the example right below says Adam determines that when Q thousand units of his product are produced each month, they will be sold at a price of P of Q equals 22.2 minus 1.2 Q dollars per unit. The total cost of producing the Q units will be C of Q equals 0.4 Q squared plus 3Q plus $40,000. How many units should Adam produce to maximize profit? What is the maximum profit that he can expect? And so the first thing to note is that we are dealing with Q thousand units, so making sure you realize that. And so we're trying to maximize our profit function, and if you notice, we do not have a profit function given to us, so we need to come up with that profit function. And so remember that profit equals revenue minus cost. And we are given our cost function up above, but we're also not given a revenue function, so we need to come up with that. So remember that revenue is equal to the quantity times the price. And so in order to come up with our revenue function for this problem, we're going to have Q times P of Q. And we are given P of Q up above. So we have Q times 22.2 minus 1.2 Q. And this works out to being 22.2 Q minus 1.2 Q squared. And then our profit function is going to be revenue minus cost. And so our revenue function, we just came up with that right up above, is 22.2 Q minus 1.2 Q squared minus our cost function, which is given to us as 0.4 Q squared plus 3Q plus 40. And so distributing our negative and combining our like terms, we get negative 1.6 Q squared plus 19.2 Q minus 40. And in order to maximize our profit, we need to take a derivative. So take a derivative, and so we're going to find P prime of Q. So taking the derivative of our profit function, which we just came up with, and I'll circle that so we can see it, we get negative 3.2 Q plus 19.2. And to figure out where this is maximized, we're going to set this equal to 0. And then solving this, we get 3.2 Q equals 19.2. And dividing, we get Q is equal to 6. And remember that Q is in thousands of units, so we'll put 6,000 units. And so that would be how many units Adam should produce to maximize his profit is 6,000 units. And then the second part of the question does say, what is the maximum profit? And so in order to find that maximum profit, we need to substitute back in 6,000 units, or just 6, into our profit function, which we have circled up above. So negative 1.6 times 6 squared plus 19.2 times 6 minus 40. And this works out to being 17.6. And for our profit, you'll realize that this is in thousands of dollars. So $17.6 thousand. And equivalently, you guys can also write this as 6,000 units and the $17.6 thousand as $17,600. The problem continues onto the next page. Part B says how many units should Adam produce to minimize the average cost per unit of production? So this time we're minimizing the average cost per unit of production. And then it says what is the minimal average cost? So in order to come up with our average cost function, which we saw back in chapter 1, this would be our cost function divided by the number of units sold, which we're calling Q for this. We are given the cost function, and that was 0.4 Q squared plus 3Q plus 40. And we're going to divide this by Q. And if you divide each of those terms by Q, this would be 0.4 Q plus 3 plus 40. And instead of saying 40 over Q, I'm going to say 40Q to the negative first. And in order to figure out where this is minimized, we need to take a derivative. And so taking the derivative of our average cost function that we just came up with, we are going to arrive at 0.4. The derivative of 3 is just 0, minus 40Q to the negative seconds. And then we need to set this equal to 0 to find those critical values of where this could be minimized. And so solving this, we're going to get 0.4 equals 40 over Q squared. I'm going to go ahead and rewrite that again. It makes it easier for me to solve. Multiplying both sides by Q squared, we arrive at 0.4 Q squared equals 40. And then dividing both sides by 0.4, we get Q squared equals 100. Taking a square root, we do get plus or minus 10. However, it can't be negative since our Q value is our quantity, and we can't have a negative amount for our quantity. And so our answer here would be Q is equal to 10. And again, remember our units were in thousands of units. And so Adam needs to produce. So we need to produce 10,000 units to minimize our average cost. It does also ask what the minimal average cost is, and so in order to find that, we're going to substitute 10 back into our average cost function, which we have. I'll circle that up above. And substituting that in, we arrive at an answer of 11. And so our average cost is cost divided by the quantity. So we have this as 11. This is in, our cost was thousands of dollars. So $1,000 over 1,000 units. And so this would work out to just being $11 per unit, since those thousands would reduce out. So $11 per unit. So that additional cost, that average cost that we would have, would be $11 per unit. So part C says how many units should Adam produce to guarantee the average cost per unit equals the marginal cost of production. So we have the average cost per unit equals the marginal cost. Remember, the marginal cost is going to be our derivative. So this would be our derivative. And then average cost, we just came up with this, which is our A of C. So we have A of C, or our average cost, is equal to our marginal cost, or the derivative. And our average cost is listed up above in part B. So that would be 0.4 Q plus 3 plus 40 Q to the negative first equals, and our marginal cost is the derivative of our cost function, which we get as 0.8 Q plus 3. And in order to solve this, I'm going to combine my like terms. And when doing that, I get my 3's are going to reduce out, and subtracting 0.4q, so we have 40 over q to the first equals 0.4q. Multiplying both sides by q, we get 40 equals 0.4q squared. Dividing by 0.4, we get 100 equals q squared, or q is equal to plus or minus 10. Again, q can't be negative since it is a quantity. And so we know from here q would be equal to 10, and again our units are thousands of units. If the revenue derived from the sale of q units is R of q and the cost of producing those units is C of q, then the profit is P of q equals R of q minus C of q. Since the derivative of our profit is going to be the derivative of our revenue minus cost, that's the same as saying the revenue derivative of that minus the derivative of the cost. It follows that the derivative of our profit function equals 0 when the derivative of our revenue minus the derivative of our cost would also be equal to 0, or saying that they're equal to one another. If it is also true that the second derivative is less than 0 of the profit function, or equivalently that the second derivative of the revenue is equal to the second derivative of the cost, then the profit will be maximized. So we have what's called marginal analysis criterion for our maximum profit. And so it says profit is maximized at the level of production of Q when marginal revenue equals marginal cost, and the rate of change of the marginal cost exceeds the rate of change of the marginal revenue. That is when the derivative of revenue is equal to the derivative of cost, and the second derivative of our revenue function is less than the second derivative of our cost function. So we have the marginal analysis criterion for minimal average cost. The average cost is minimized at a level of production where average cost equals marginal cost. That's when A of C of Q, or average cost, is equal to the derivative of the cost, and we saw that in the previous example. The next idea that we have is called elasticity of demand. Elasticity of demand, the change in price of a product or service will change the demand of that product or service. One way to measure the sensitivity of demand to change in price is by the relative change, the ratio of percent change in demand to percent change in price. Let Q equal F of P, where Q is demand at a price P. The elasticity of demand is given by, and we have a formula here that we do need to know, and it's E equals negative P over Q times the derivative of Q with respect to P. And then we also need to know these listed down below. And so what this says is that demand is inelastic if E is less than 1. So what this means is going to be a small change in price has little effect on the demand. And then demand is elastic, or E is greater than 1, which means a small change in price has more effect on demand. Demand has a unit elasticity when E is equal to 1. So remember that total revenue is maximized at a price where demand has unit elasticity, and remember that revenue is the price times the quantity. So the example right below says, suppose the demand for a certain beverage is Q equals 24,000 minus 3P squared, where P represents the retail price of a case of the beverage in dollars per case, and Q represents the average number of cases purchased per year by a consumer. Calculate and interpret the elasticity of demand when P is equal to $50 per case. So in order to find our elasticity of demand, I'm going to go ahead and write down that formula that we have that's given up above. And so E is equal to negative P over Q times dQ dP. And so we know what Q is. We know Q is given, and Q is equal to 24,000 minus 3P squared. And we can easily find dQ dP by taking the derivative, and we arrive at negative 6P. And so setting up our elasticity of demand formula, we have negative P over Q, and instead of Q, we're going to write 24,000 minus 3P squared times dQ dP, which we just arrived at as negative 6P. And so from here, we get 6P squared over 24,000 minus 3P squared. And so this is our elasticity of demand function. And we want to know what the elasticity is going to be when the price is $50 per case. So we're going to evaluate this when P is equal to 50. So substituting in 50, we arrive at E equals 6 times 50 squared over 24,000 minus 3 times 50 squared. And working this out, we get E is equal to 0.909. And so E is less than 1. And when E is less than 1, the demand is going to be inelastic. So demand is inelastic. And that means that for this beverage, a small change in price has little effect on demand. So the next example that we have, we're going to go ahead and circle, and we'll look at this one together in class.